So hello everyone, I'm Ricardo from the Mathematical Computation Group of Wolfram Research. Today I'll be discussing a bit of research talk about applications of neural networks for partial differential equations. So I'll just talk about why the use of neural networks for partial differential equations, what is a neural network, and then what are physics-informed neural networks. Then two more advanced theoretical approaches for high-dimensional partial differential equations. And then that will be the end of the talk. So let's start by why to consider neural networks for solving PDEs. So currently, we have very good methods for solving most of partial differential equations. That would be like the finite element method, for instance. But there are also new approaches that use neural networks to solve PDEs. And one of the advantages of neural networks are that they do not rely on a grid, so that they don't need to be discretized. Also, they don't suffer from the curse of dimensionality, meaning that you can increase the number of dimensions of the problem, and the problem would not get, in most cases, as complex as with other methods. Also, they are more efficient evaluating in new data points once they are trained. So what is a neural network? In essence, as we will see later, a neural network is like a big equation with a bunch of parameters that you will adjust to get your desired solution. But what are the components of the neural network? A neural network is composed by neurons that basically take inputs and hold a number based on those inputs. So, for instance, in this example, this is what a neuron is doing essentially. Is taking three inputs, multiplying each of them by a weight, and then plus a bias, a number, and then all of that is squeezed into what is called an activation function. So in essence, each of the neurons is doing this operation, and in the end, each of these weights and biases are parameters that we will adjust to get our desired solution. So the structure of a neural network normally is you have an input layer and you have hidden layers that are layers in between, and the number and the architecture of these hidden layers depends of the problem you're trying to solve. And in the end, you will have an output layer that is related to the output that you would want. So, for instance, let's take the example of that you're trying to identify handwritten digits. So in this case, if you look down below, you could see that we have an image and the corresponding handwritten digit that we will want to classify. So in this case, we will need, for example, a neural network of the number of pixels of each image, and each of the the values of the input neurons would be the values of the corresponding to the value of the pixel of the image. So in the end, we will have, in this case, a bunch of parameters. In this case, it could be as much as 13,000 parameters that we will need to adjust. And how do we get the desired output? The desired output we could get basically by training the model with data, like we have here. So we will compare an output that initially would be just random values at the end of the neural layer, sorry, of the neural network, and we will calculate the cost of each output in each of the iterations of this process. So for instance, we will take the values of the neurons in the output minus the desired output, and summing of those squares will give us a number that is the cost of that iteration. And in each iteration, we will try to reduce the cost by turning the parameters of the neural network. So, for instance, what is physics informed neural network then? So it all comes to the cost function. So as you know, many of physical phenomena is modeled through PDEs, and in the end, you will have that we will integrate these PDEs into the cost function. So, for example, for a classical neural network, you will have an input. Let's say you're trying to solve a one-dimensional partial differential equation or a differential equation. So you will have as an input the value of x, and as an output, you will have the value of the dependent variable that you're trying to solve for. You will give it some training points. In this case, let's consider a damped harmonic oscillator. So you will have some training points, and the cost function reflects that. But the thing with physics informed neural network is that you are also adding the residual of the partial differential equation you're trying to solve. So basically, this part is related, is eventually going to be zero. So when you minimize the cost function, you are making sure that the solution of the neural network follows the solution of the differential equation. So let's take a look at that. How would that look? So we could see here that for a classical neural network, when you train it, it accommodates very well to the training data, but it doesn't do a very good job where there is no training data in those regions. But for the physics informed neural networks, you can see that for this example, it gives a really good solution for this problem when in the regions where there is no data. So for example, if this is just a result for the Burger's equation, and here the training data is on the boundary. So basically the Dirichlet condition for your PDE will give you the training data that you will then use. And as you can see, the physics informed neural networks network does a very good job in the region where there is no training data. So if you want to see how does this look in the Wolfram language, you just need to go to this post that I will leave here, so you can check it out. But I would like to talk about some more advanced methods that are really useful for high dimensional partial differential equations, and that is where this is even more useful because traditional methods like finite element method do not do a great work with high dimensions. So the first one is the deep BSDE method, that stands for backward stochastic differential equation. So this method is good for parabolic PDEs, nonlinear parabolic PDEs, and of course it doesn't suffer from the course of dimensionality. So the parabolic differential equation that we would want, nonlinear parabolic differential equation that we would want to solve is this one that is right here. So this is our goal to solve this, where x is not the usual spatial variable, but it's a d-dimensional space variable. So this can have many dimensions. Mu is a vector valued function, as well as sigma is a matrix value function. Hess is the Hessian, and f is a known nonlinear function that we will want to solve. So let's say that w is Brownian motion, and that xt then would be a stochastic process that will be given by this integral equation. Then using Ito's lemma, we could prove that the solution to our parabolic differential equation is given by this equation right here. And we could inspect this expression and see that for the value of the gradient would be the most difficult thing to obtain in this equation. So that's where we will use neural networks to approximate that. Here, also as a first step, before using neural networks, we will just approximate this integral equation that is actually a backward stochastic differential equation, therefore the name, as using Euler's formula as this equation right here. Sorry, here. So here we just taking small steps in time and small steps in W, that such that we can approximate that this way. So let's use now neural networks to solve this. So we will define the grading at times of the initial time and the function at the initial time as parameters that we will then train. And then with x and w, we would take that as an input and put it in a neural network with h hidden layers that is represented in this region right here. So with x, we will get, by training this neural network, we will get the gradient. And then with the gradient, we then can use the equation we just saw and obtain the value for the next for the next time. So of the solution that we're interested in. Then we will repeat that for each of the times. So we will build a bigger neural network from that. And then we will have at the end, or the value of u evaluated at the final time, at the final position. So in the end, we will have these two parameters that we define that are corresponding to the initial solution and the initial gradient, and each of the parameters corresponding to each of the sub neural networks. And our loss function will be defined by a terminal condition, meaning that we will need to know the value of the solution at a final time, and then we will train the neural network by taking the difference with the solution evaluated for the whole path taken. So yeah, basically this is the deep backward stochastic differential equation method. And to end my presentation, I just want to talk about the variational quantum Monte Carlo method that specifically is targeted to the to solve the multi-particle Schrödinger equation. So using the Bohr-Oppenheimer approximation, you will have a Hamiltonian that could be written like this, and the corresponding eigenvalue problem. So the main idea here is to approximate the solution of this Schrödinger equation by proposing an answer that will depend on some parameters theta, and it will be given by the combination of the linear combination of Slater determinants that have an orbital molecular part and an envelope function part, and each of them depend on some parameters that we will train. So here we're using the variational principle of quantum mechanics that tell us that the expected value of the energy will be, once minimized, will be corresponding to the value of the ground state. So here in each iteration, we are evaluating this integral, and the values of R are chosen by the Monte Carlo method and are distributed according to the probability density given by the current ansatz. So this basically means that in each iteration we are choosing random, but not random, but points that are distributed accordingly to the current ansatz, and then we are updating those parameters for the next iteration. So in the end, we will have a neural network with a loss function that will be equal to the expected value of this local energy. That way, we will, in the end, get the energy corresponding to the ground state and the energy and with the ansatz and its trained parameters, then we'll get also the function for the ground state. So this has been what I've been researching, and I hope you find it useful. Thank you. Okay, so here is one question. When using a neural net model, a neural net to model the PDE, have you ever used less than 32-bit floating point for the weights and activation of the neural net? So this is a bit of an ongoing research project. So I don't have a clear answer for that yet. I've been exploring what people have done until now, and what are some what are the most used methods, and I explore some of the solutions people have come up, but I don't have anything like concrete yet. Where you input the problem differential equation. So well, I think I don't understand that last question I read. What do you use the nonlinear function when modeling a PDE with a neural net? So the nonlinear function is used. I think I can show you. So here, the nonlinear. I think you're referring to this. This is the nonlinear function for the PDE. So in the end, the solution that we are approximating depends on that solution, on that nonlinear function. So in each iteration, you are using this in this step of the diagram. once you have the gradient, you're using this equation to get the next value of the function of the dependent variable. Yeah. Other question is, one hurdle for me trying to use the Wolfram language for physics in for neural network has been that net-port gradient only supports first order derivatives. How do you overcome that? So unfortunately, I couldn't overcome that because there is a limitation in the framework. And what you could do that would maybe help is to approximate the second derivatives using uh, basically approximation formulas for the second derivative. But you could not calculate it straight away, unfortunately. So someone is asking if what are the nonlinear function. What I think that depends on the type of PDE you're trying to solve. So, for instance, the backward stochastic differential equations method is used for finance, mainly for finance applications. So those type of equations, I will give you the type of nonlinear function that you're trying to use. Next question says, are Kolmogorov-Arnold nets any easier to implement than an standard MLP? So I sorry, I'm not familiar with those terms, so I couldn't answer that. Sorry. Mm, yeah. So Adma is saying, where do you input the problem differential equation? So I don't know, but I think I'm not 100% sure if I understand the question. Maybe could you rephrase the question a little bit so can maybe give you an answer? So at least in the case of physics informed neural networks, you will plug, sorry, you will plug that in this term of the loss function. So you will, here you have two terms. You have a term that depends on the training data that you have. In the case of the harmonic oscillator, is the training points that are shown here. Although maybe there you cannot see very well, but here these points. But the green part is where you would write the terms, the residual of the partial differential equation that you will try to solve. So there, that would be the answer for. Um, Another question is, have you used a rectified linear ReLU or for nonlinear function when modeling a PDE with a neural net? So if you're talking about the activation function, at least I see that for physics informed neural networks, you could use uh, activation functions that reflect what the problem you're trying to solve. So for instance, if you're trying to solve an equation that maybe has a solution that you can have some intuition about the solution, you can then try to use activation functions that mimic that solution. So for instance, let's say you're solving a heat type equation, so you will then use activation functions that are similar to the terms that you will get in a general solution of the heat equation. For instance, something similar to a sine. If you are, I think you get the point. So I think we are coming to the time. Many of you will probably want to go to the next talk. If I think I can type it in the chat. So if you have any questions, feel free to email me. And thank you for being here, and thank you for the questions. Bye.